So good morning to everybody. So did any of you try to reverse a stone on the way down to see if something is underneath? Huh? No? You should try. Maybe there is something underneath. So okay. So let me start. We have 4 hours. I hope that you would not hate me after that. And so yesterday we said that there is this okay, there is this conservation law, okay, and yesterday I put a 4 here by mistake. The 4 is here, not here, okay. And he said, okay, if this is the anomaly, chiral anomaly in 1 plus 1 dimension. This is the difference of charge between the two parts of the spectrum, okay? These two parts of the spectrum, okay? And then we said, okay, if I integrate this in space and time, okay, then I get that as a special case, I get delta Q tilde equal to 2, which is moving one electron in each side, up, one side up, the other down. The spectrum returns to itself. And in fact, if you also integrate this on a cylinder, you discover that the value of the gauge field on top and down differ by a proper gauge transformation, so you can compactify it, and so you can make sense of this quantity that is now defined on S1 cross S1. Okay, this quantity now is well defined on S1 cross S1, and it takes an integer value. Okay, which is the monopole. Or if you want, if I insert flux, quantum of flux, this corresponds to changing exactly the charge by this, and this corresponds to the spectrum of the Hamiltonian going to itself. Okay? As we said the Hamiltonian with one extra flux, phi naught, is equivalent to the Hamiltonian, equivalent in the sense of a gauge transformation, which is a large gauge transformation, and large gauge transformation is not well defined. So large gauge transformation is periodic for you, but not periodic for lambda. Okay, and we said, okay, well, what counts more? Should it be well defined U or lambda? Well, it is U that should be well defined, because the gauge field a mu appears into the exponent in the path integral, in the wave function. Okay, so what really matters is that this is well defined, and this could be defined up to 2 pi integer. Okay, that's at the end of the story. So so if you say in classical physics everything depends only on the electric and magnetic fields, in quantum mechanics also something depends on a mu, okay, not only on a and b, but it depends on a mu, but it is at exponent. So there is a dependence on a mu, but it is an exponent. Okay, that's at the end of the story. Okay, so quantum physics, you have dependence on the gauge field, but it is at exponent. Okay, this very simple observation is a Dirac observation, so that's why it is called the Dirac phase, and I think it's around 31 or 36, I don't remember. Okay, so now we are going to discuss more the consequence of this, okay, and to discuss the monopole field in a different geometry, which is the sphere. Okay, that we see better this fact that there is a quantization. So that this quantity is, that in some cases this quantity is e to the 2 pi n, okay? This is also called geometric quantization. Quantization. Okay? So let's now discuss how this fits with a monopole on a sphere, okay? So just a second. Please, you say, yes, please. Because delta Q is 2, and this is 1. Minimal value is 1, and this is minimal value 2, because you have two contributions, one from here and one from here. Okay? And we managed to do the gauge transformation yesterday, and this was well defined. And the normalization of the gauge transformation is here, you see? This is non-trivial one should be e to the 2 pi. The minimal value should be 2 pi. So this is normalized by this. The gauge transformation of f is normalized by this. So everything is normalized. There is no ambiguity. There is no choice. Yeah? This or here? Okay, maybe it was a mistake. You know, you can also write as 1 over 2 pi. There are a factor of 2. Okay. Okay. So let's discuss a monopole. How do I make a monopole? Well, it's very easy. You take a solenoid, okay? Then you know that the flux liners of B field are like this, okay? Okay. So okay, these are two wires, okay? So how do I get a monopole? Well, I squeeze it and I send this extreme towards minus infinity, and I forget. Then you're left with a very thin solenoid up to a point that is x equal to 0, and the field around this, it looks like the field of a charge, of electric charge, okay? That's a monopole. But does it make sense? Well, let's see. Okay, let's see. Okay, so the flux around this point has to be a definite value. So the flux will be, let me call the magnetic flux G over S2. Okay, you have B ds. Okay, okay. So now, but there is also a contribution from the string here. Okay, so this goes away here, but this enters like this. Okay, so a solution for B is G over 4 pi r square r plus G theta of minus z delta of x delta y direction z. Okay? Okay? this, you see, is a thing that is pointing. This is a area of the sphere. So if you integrate this, you get G. Okay, here. But then there is also a contribution minus G from here. Okay, you see, because when you integrate, you get a step function, delta function. Z is pointing down. So sorry, it's pointing down. Yes. Pointing down or pointing up? Yes, because you have to do a derivative, yes. It's like this. So you eventually you get that integral of this b is g minus g. So this can be represented by a vector potential, okay? So let's compute this vector potential, okay? First from the first piece, so you want to do A, want to solve this equation for A, okay, okay? And you want to solve in R for with the exclusion of the string, okay? So let me compute this with the exclusion of this string, okay? Okay, so let me integrate A along parallel, okay? So I'm going to use I'm going also to use the polar coordinate theta and phi, okay? So I'm going to compute integral of dx mu a mu on this parallel gamma, okay? So is this going to be ds a, okay, on a surface sigma such that this sigma is equal to gamma. And which sigma should I take? I should take the upper cap here because I want to avoid the problem of, yeah, so sorry, yeah, the center was here, otherwise, okay? I want to avoid the problem of a string here, okay? So I take the upper cap, okay? And this will be 2 pi a phi. So I also use a mu in component a phi a theta, okay? I assume that I try to solve for a theta equal to 0 and a phi is a phi of theta. Let me try if I can do this, okay? Okay? Okay, but so this is also g over 4 pi, the, the solid angle evaluated on sigma, okay? Okay. Okay. So what is the solid angle? Well, the solid, I continue, okay? The solid angle over sigma is integral of d phi between 0 and 2 pi, and integral of 0 and theta of d theta sin theta, okay? So that's going to be 2 pi 1 minus cos theta, okay? And this is equal to 2 pi a phi of theta, okay? So I found a phi of theta. No, sorry, there is a g phi, okay? So this is going to be okay. No, let's do like this. So this is 0 and okay. Now I want to get from these components to ordinary components. So I have to remember that on the sphere, the length element is okay. Sorry. Okay. And so if I want to make a vector a modulus square, this is going to be a phi g phi phi a phi. Okay. Okay. So I have to divide by g phi phi is 1 over sin theta square. Okay, from here. Okay. So in the end, the gauge field of the monopole in ordinary coordinates is g over 4 pi 1 minus cos theta divided by r sin theta, direction phi. Okay? That's the solution. The solution of this equation of where is it? Yeah, this equation there. Okay? Okay? But then there is a problem. There is a singularity somewhere. Otherwise, there is a, I mean, could get the integral of this function equal to 0. No? There is a singularity. Let's see. So this is a solution, but you see, for theta going to 0, you get theta squared divided by theta. It is regular in the upper pole. But when you go to theta equal to pi, this is 0 and this is 2, so it's singular at theta equal to pi in the south pole. Okay? So this is solution, as I said, in R minus the north pole, the south pole. Or actually the entire string. South pole in the sphere, but the entire string in R3, okay? Okay? Okay. Okay, but then, you know, there is another solution. There is another solution because when I rewrite the contour integral in terms of a surface integral, I can choose that the surface, the upper cap or the lower cap. So if I put the string on top, okay, if I put the string towards, if I put the string here, I could put the string here, then I can integrate this loop gamma over the south cap, okay? So in this case, integral of d omega is integral from theta to pi of d theta sin theta, okay, and d phi over, okay, and this is 2 pi minus cos theta minus 1. So there is another solution, A, which is minus g over 4 pi r, 1 plus cos theta divided by sin theta phi. And this solution is for R3 minus z bigger than 0. Okay? So let me call this A minus and this A plus. Okay? So there are two solutions. So this, let's check that this solution is now regular for theta equal to pi, okay, because this goes to 0 and this also goes to 0. Instead, it is singular for theta equal to 0. Okay? Okay? So I got these two solutions. Okay? Got these two solutions. So what's the point? The point is that if I superpose them, if I consider them and compare on the equator, they differ by gauge transformation. Let's check this. A plus phi minus A minus phi is what? Is G over 4 pi 1 minus cos theta plus 1 plus cos theta, which is G over 2 pi, which is d phi lambda of phi, and lambda of phi is G over 2 pi phi. Okay? And this is a proper gauge transformation because, again, we find this business that is a large gauge transformation because u, which is e to the I lambda, is u of theta, u of, u of phi, okay, is e to the g over 2 pi phi, okay? And then there is, in fact, there is a electric charge here that I forgot. And so this is for u equal to 2 pi, I get e to the I g e, okay? That should be u of 0, okay? And this is possible if GE is 2 pi h bar n, okay? And this is the Dirac quantization condition. So the conclusion is that the string is invisible if this the gauge transformation is proper gauge transformation if the magnetic charge and the electric charge obey this quantization condition. At the same time, the string is invisible for a test particle. That is a calculation we did the other day. If I take a test particle, I have I get this phase, no? A, which is, okay, there is a C here also. I get this flux, so this is, the flux is EEG over H bar C, that's just to be 1, 2 pi, and so I get the same quantization condition. So the invisibility of the string for a test particle is the same thing as the fact that the gauge transformation that connect the two solutions here is a proper gauge transformation. Okay? Okay? So now you have the possibility to forget about the string and say, okay, I forget about the string. String does not exist because a test particle doesn't see it. Or if you want, the Aronoff bomb phase is 0, or it's integer. Okay? Aronoff bomb phase will be when this is not satisfied. In this case, there is no, Aronoff bomb phase is integer, so the test particle will not see the string. In more modern way, we say, okay, in this case, the field, the monopolar field is described not just by a vector potential, but by a pair of vector potential. Each one is defined on an open set, of the sphere, and to cover the sphere, you need at least two open sets. And the condition for consistency is that the gauge field on the two sets, when you connect, should be connected by a proper gauge transformation. Okay? So in more mathematical words, we see that, as I anticipated yesterday, that F, which is a two-form, is closed. This is Bianchi identity, okay? In fact, this is true, strictly speaking, for x different from 0, okay? Because x equal to 0, there is a singularity for f. But f is not exact. But more precisely, f is exact on each patch. So is in this upper cap that I call sigma plus, or if you want, the 2-disk plus, and this is the 2-disk minus. Okay? And A plus minus A minus is a proper gauge transformation. Okay? Okay? So you have a non-trivial differential bundle, because the gauge field has this singularity. So the bundle is given by some manifold M, which is the base space. In this case, this is S2. Then you have a fiber, which is a vector space. In this case, it's a U1 vector space, because this gauge transformation, there is an element of U1. So in any point of space, you have a U1, which is called the fiber. Then you have the A mu, which is the connection, that tells you how to do the covariant derivative from one fiber to the other, okay? So that's a geometric description. So it's a non-trivial fiber bundle, or differential bundle, fiber bundle, I don't know the name precisely. Fiber. Okay, non-trivial. Okay, so what I wanted to say, yes, and okay, that's it, yes. And can I do quantum mechanics with this gauge field? With this gauge field? Yes, you can. You do quantum mechanics with A plus on the upper part, and quantum mechanics with a wave function, another wave function in the lower part, and then you reconnect. Physical quantity should be gauge invariant. The two are connected by gauge transformation, no problem, okay? And this is so-called Wu-Yang monopole. This is a very nice paper by Wu and Yang. This is 76, so it's not so long ago after all, okay? You can read nuclear physics. Okay, they argue that this is a proper way to describe the monopole without string. Okay, and you can do quantum mechanics on it. And the funny thing is that this gauge field of the monopole contains angular momentum, which is 1/2. You can work out what is the angular momentum of this gauge configuration. It is 1/2. Well, say, if this is just for charge 1, okay, or angular momentum is n h bar n half, okay? That's a funny thing, okay? Okay, so that's the end of the story. So it is a non-trivial gauge field, cannot be described in a single gauge. You have to do two different gauge choice on two different open covering of open patches of the sphere, at least two, okay? That's the story, okay? Yes, please.
If I understand correctly, here the gauge field doesn't describe the string, right?
No.
It's only the magnetic monopole.
Yes, the string is put under the carpet, okay? Because you in one patch you put a string on the opposite part, and in the other patch you put on the other. So you don't speak about the string, okay? So in the end, the only singularity that is really important is in the center. This is the only singularity. But you are describing the field on the sphere, so there is no singularity on the sphere. Funny, eh? Please. Yes? No, no, I made it local. But with two fields. No, no, it's local. The only thing is that I don't describe it with one gauge field, but two gauge fields. Okay? Okay, so now the question is, do monopole exist? Well, we don't know, because this argument this is a static classic source, okay? It's a source, so you don't know which dynamic this thing has. Which is the mass of this guy? If this mass is, 1 million solar masses, it's not very easy to see, okay? So we don't know from this argument, okay? Maybe it exists in some cosmological model somewhere, but there is a very nice thing that Dirac noticed, that if the monopole exists, then and has some charge G0, then this implies that the charge is quantized. Okay? Charge quantization. So why charge is quantized? Nobody knows. But if there is a monopole somewhere in the universe, you can send an electron to make a tour around it, and for consistency, then it has to be quantized. Okay? No, what is quantized is the product. So you say either way. Either way, yes. Yes. If charge is given, then the monopole charge is quantized, and vice versa. Okay? Okay. So, okay, that was not so bad. Too fast? Okay. Now we go to another. Yes. Yes, please. Yes.
I mean, you said that the mass of the monopole, you mean that the particle is acting as a magnetic monopole that mass?
Yes. 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 So this is a classical source. So I put it there. I don't know what it is. It could be, I don't know, gigantic alien spaceship. I don't know. eh? So they don't exist. I think they searched for them in some LHC in collisions because the highest energy you can reach, and they didn't find. But maybe they exist in some cosmological model. Okay. Then, nonetheless, we can make it. And now I'm going to discuss another issue, which is the same thing, but it's called the Berry phase. It's the same thing. Why is the same thing? Because eventually you are talking about a non-trivial U1 bundle, and there are not so many non-trivial U1 bundles, just one, because there is only one quantum number, only one quantization condition, which is the first chain class or the monopole charge. It's only this thing. So for U1 gauge field, there is no more than that. So I'm going to discuss now another instance in which you get the same field, but this field is not made by an external. It's not an external source, but it's coming from the parameters themselves of the Hamiltonian. That's the Berry phase. Okay? Maybe you know something about the Berry phase. Yes? 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 Because the direction of the string is anywhere. You choose where to put it. Yes? 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 To integrate over the lower part, I should put the string up because the string is a singularity. Okay? So, yes, yes. The string can go anywhere, okay? Because in order to be described by a gauge field, A, the total flux should be 0. So you have this smooth flux, and then then which is positive, and then a singular negative contribution somewhere on the sphere, and that's where the string passes. Okay, you can put the string down, up, where you want. Okay. Yes. 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 You can put the string from 0 anywhere. And what is the choice? The choice that allow me to do this integral without singularities. Yes. 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 So the gauge field, the A is defined up to a gauge transformation. The magnetic field is the same. Yes. Yeah. Please. Yes?
So it's like if the string brings the flux from, because the string is attached to infinity.
Yes?
So it's like if the string takes the flux from infinity and bring it
Yes?
to generate the manifold.
Yes?
And so this is a non-locality.
Yes?
You say that you can do normal quantum mechanics with this operator.
Yes?
But that is non-local, doesn't have any concept.
No, because you use two gauge fields. So you do quantum mechanics on the upper part, and then another quantum mechanics in the lower part. They differ by gauge transformation. The wave function differ by gauge transformation. So you don't have wave function, but have two wave functions. They are called sections of a fiber bundle. So you have two, and you work with this. When you compute something, we will be related to electric and magnetic field. They're the same. Okay? So this is this paper. And this guy is the same of Ian Mills, okay? Apparently in the 60s and the 70s, he was very much interested in these quantization conditions. Yes? That you have to use two patches. No. And then the language of fiber bundle is the proper thing. Dirac didn't know. But he had everything right, okay? So Dirac understood that this essential point that quantum mechanics has a mu as a variable, not the electric field, the magnetic field of classical physics, but this a mu is to the exponent. So it can have two pi different 2 pi phases. Is a phase, so it is defined up to 2 pi. It need not to be well defined. It can be defined up to 2 pi. Okay, as simple as that. Okay, now discuss that in fact this same field appears into a simple quantum mechanical problem, but is a field not external but made from the parameters of the quantum mechanical problem. And this is due to Berry, so I think it's still in the 70s, a little bit later. It's a very simple model. Why I discuss this? Because we use both ideas when we discuss topological state of matter. We use both ideas, okay? It's very simple. So you take a spin in a magnetic field. So you have a magnetic field, H, and you have a spin degrees of freedom, okay? So the Hamiltonian is H, okay? Okay, then sigma are the Pauli matrices. Okay, and what are the eigenvalues? So it's a two-dimensional Hilbert space. So the states are two spinors, constant two spinors. Okay, alpha beta. Okay, so what are the eigenstates? Well, very easy, because if you take h square, this makes h square because of Pauli matrices. Okay, Pauli matrices sigma I, sigma j, delta ij plus I epsilon I j k sigma k, that you know, I guess you know. Okay, so then it is a two-dimensional space, so the eigenvalues are plus or minus h. Okay, so let's compute alpha and beta, this vector. Okay, well, it's very easy. You can use because you can take h is a constant value, okay? In absolute, you can divide in absolute value h, okay? And use the polar angles to describe the direction, okay? So you have h1 is h sine theta cos phi, h2 is H sine theta sin phi, and H3 is H cos theta. Okay? So we have a parameter space which is again a sphere. Okay? So H is pointing in a direction which is characterized by the polar angles, okay? And sometimes called the block sphere, or forget about names, okay? Okay? So now we don't have this ambient space, but we have a parameter space. Parameter space characterized by theta and phi, which parameterize the magnetic field, okay? So what is the eigenstate? The eigenstate is easy to find because the Hamiltonian is cos theta minus cos theta sin theta e to the minus I phi and sin theta e to the I phi. And you have, let's take the upper eigenvalue, okay? Upper eigenvalue. The upper eigenvector is you can work it out, okay? Okay, that's the upper eigenvalue. And this is a free phase that you can put. You can put a free phase at your choice. Okay, so then there should be a singularity in this business. And there is a singularity is that this eigenstate is not globally defined. In fact, if you evaluate to theta equal to 0, it is e to the I alpha 1, 0. If you evaluate at theta equal to pi, it is e to the I alpha 0, e to the I phi 0. Okay? Okay? Well, now you say, let me fix alpha equal to 0. So this is well defined. But then this is not well defined at theta equal to pi because this is multi-valued in a single point. At the North Pole is, so if I take alpha equal to 0, I get, this is at the upper pole, North Pole is well defined, but the lower pole is not well defined because it is multi-valued in a single point of parameter space. Or I can say, well, let me put alpha equal to minus phi. Then it is e to the minus I phi 0 and 0, 1. So this is now well defined at the lower pole, at the south pole, but not well defined, multi-valued at the upper pole. Okay? So in this, so you see this eigenvalue problem cannot be globally defined, is not in a non-singular way in the entire parameter space of this Hamiltonian, which is theta and phi, the sphere made by theta and phi. Okay? So you have a U1 fiber bundle because this is a U1 vector. Okay, the spinor is a complex the spinor is a complex number. You have this sort of free phase, which is kind of a sort of gauge symmetry, gauge U1 symmetry, sort of U1 symmetry. Okay, that at your choice. And so if you have a U1 phase, you can say, can I define a connection for this U1 phase? And this connection will have the same properties of showing a monopole. Yes, I can, and this is the Berry connection. How do I go? Well, I'm not sure I will be able to cover the subject in 5 minutes, but let's start. Well, the idea is to do the idea is to see what happens when I do a adiabatic change of parameters in the Hamiltonian. So you say, okay, the phase is arbitrary. It's true, it is arbitrary. So what will be relevant is not the phase itself, but how the phase changes from one case to another, from one value of the parameter to another. So rotating the magnetic field. Okay? Okay, so then you have to imagine to do adiabatic change of the magnetic field slowly in time. Okay? So you say H depend on time and slowly. Well, why slowly? Because you don't want to change, you don't want to create an excitation. If you make an abrupt, so you have a two-level state. If you make an abrupt change, you can jump from one, the state can jump from one state to the other. Okay? As before also in the spectral flow, you want it to be slowly because otherwise you could create excitation out of the Fermi sea. No? If you do slowly, the state remains the same. But what can happen? It can accumulate a phase. Okay? So adiabatic change, which will be the solution of the Schrödinger equation in adiabatic change. Well, I take, now it's a bit tricky, so be careful. So I take the instantaneous solution of, okay, first of all, I consider the upper, so I consider the upper eigenvalue, okay? Let me put the system in the upper eigenvalue, and I subtract the value h, okay? So let me define h prime like h minus h, okay? So h prime on h makes 0. This avoid me a trivial phase, okay? Okay? Then I say, I have an instantaneous, at any given time, I have a solution of this problem. So I have a solution this is instantaneous eigenstate. Okay? But then I say, okay, this is instantaneous, so any given value of h, I have this solution of the stationary state. But the state, if I vary in time, the state is not stationary. So there will be a time-dependent solution of the Schrödinger equation. Okay? Okay? Which will be the wave function of the solution of a non-stationary Schrödinger equation that I have to use because it's not the same. Well, it will differ by a phase with respect to instantaneous solution. Okay? So this is the true solution at any time. And this is instantaneous solution. There is a phase. Okay? Because if I move slowly, I will not make a jump of eigenstate. The eigenstate will remain the same. What it can get? It can get a phase. Okay? If you don't believe this, you go to book of quantum mechanics and you find that you can solve completely the exact solution with varying in time h and take the adiabatic limit and find this. So I tell you where it is. Griffiths. Quantum mechanics. Introduction to quantum mechanics. and Sakurai, appendix of Sakurai. Okay? Okay? Okay, now let me continue for a few things, okay? Okay, so I consider the following equation: psi dot. So this obey psi dot equal to IH psi, okay? Okay, so that will be U dagger U dot plus H dot, okay? But because H psi is 0, okay? This is 0, this is 0. Okay, this is psi H psi, it is 0. It is 0, okay? So the phase I'm looking for, which is the phase I'm looking for is okay? It's a parametric variation in time with these velocities, this phase, okay? And I can represent this phase as a gauge with a gauge connection. Yes. A gauge connection represent, so this I can write like U exponential of minus I AI lambda I dot dt, okay, where AI is minus I H, okay. Okay. Definition. Okay. So what is the result? If I do a adiabatic change, the phase of the wave function changes. This phase can be obtained by parametric variation of the instantaneous solution of the stationary problem, and is obtained by a derivative with respect to parameters of the eigenstate of this overlap. Okay? Okay, maybe now I stop because I have some more consideration to make. So by varying adiabatically the quantum mechanical problem, I have a phase, and this change of phase can be represented by a kind of gauge potential or Berry connection, which is obtained from the parameters of the Hamiltonian. Okay, I cancel the general solution was H cos theta e to the I phi sin theta half, and H prime, let me call H plus H minus e to the minus I phi Okay. So the one was singular at theta equal to pi, and this is singular at theta equal to 0. Okay. Okay. So now at this point we can compute them. Okay. Compute is A. Okay. Okay. So then you say, okay, you just do these derivatives. Okay. A theta is minus I h derivative respect to theta h. Okay. Let me use h plus. Okay. Okay. I have to do this derivative. No, it's not so difficult. Okay. Let me put it the solution. 1/2 0 a phi is okay. Okay. You start to see that it's the same thing of before. You see, a plus. And if I compute for the other thing, for h minus, I get this is again 0, but this is different. Okay. So we came up with the same gauge field as in the monopole. Okay. So what is the value of the charge here? The value of the charge is we compare and we see that G. Let me cancel this. We compare and we compare with before. We say, okay, what is the value of the magnetic charge here? 4 pi equal to 1/2. Okay, so let's put electric charge equal to 1. So that will be G equal to G minimal value, which is G equal to pi, which is n equal to 1. So in this system, I have a gauge field which is correspond to magnetic charge equal to 1. Okay, electric charge is not important here. Okay, and I can also define the Berry curvature. Berry curvature f theta phi is d theta a phi minus d phi a theta, and this is 1/2 sine theta. Okay, and the integral of S2 of d theta d phi of, let me call f, okay, f theta psi is 2 pi 1/2 times 2 is 2 pi is the volume. You see, this is a volume. This is a volume form, 2 pi. Okay? So it's like a monopole. Again, the two differ. The two differ by the two gauge field differ by gauge transformation. So the two, the two solutions of where did I put? I canceled them. The two solution of so to summarize the summarize the quantum mechanical problem is not globally defined. You have a eigenstate which is singular somewhere. If you want to avoid this singularity, you have a possibility to add the phase. Okay, this phase is arbitrary. Okay, but there is an effect. The net effect is that if you take an adiabatic change, and after this adiabatic change you return to the same point, just to compare. Okay, then you will get if you close this contour. Okay, if you close this contour, so that means you return to the same state. So you vary the magnetic field, the direction of magnetic field, you make a tour, and then you return to the same state. This object is gauge invariant, so it's well defined, and so the adiabatic change of a state has obtained a well-defined phase, free arbitrariness. Okay, and this phase define a connection which has a curvature, which is again the discharge, which is again the first Chern class. Okay, so that tells you that some systems, Hamiltonian of some systems, may have inside, in respect to the parameter space, the same features of this non-trivial monopole, non-trivial gauge field, but it is issued from the parameters of the Hamiltonian, not from the external field. Okay? And this effect has been measured. So it's such a simple problem. No, it has been measured. Of course, you cannot measure any time. You have to do this adiabatic change, because any time, at any given time, the phase is arbitrary. What you have to do is to obtain something which is gauge invariant. So you have to make a loop in parameter space, come back so that this phase is unambiguous. Okay, so you have to do an experiment that compare the wave function before the adiabatic change and after, which is kind of not completely trivial, no? So usually you do quantum mechanics. I do a measurement now, and I compare. No, this is not the same thing. You have to compare something which was before. So it's a kind of new idea, no? That in quantum mechanics, and you measure this effect. Okay. So that's the end. So why is this important? It's important because some system will show this anomaly and topological features because you put an external magnetic field and you put some background, and that will be the response of the system to a background. But you could also get this topological feature in a system without background, but somehow this effect is inside the Hamiltonian. Okay? And so anticipating a bit, you will have some, for example, band system, so free fermion in a band system, I mean, usually in a gapped phase. Okay, you have a conduction band and a valence band, and you put the Fermi surface in between. So it's insulating phase. Okay, insulate is an insulator. Okay. Okay, so then you can represent the two bands like this simple two-state system, like a spin, and then you will find that sometimes this band state, band material, will develop a Berry phase with topological features. Okay? Okay, now we switch to another subject. Then we return. So I mean, that was somehow the math behind this, and I wanted to present you in the simplest, let's say, quantum mechanical or simple systems. Okay, just to have in mind, to keep in mind what is what is all about. But then we go to more specific analysis of the Dirac Hamiltonian. Okay. So Dirac Hamiltonian, I'll try to be a bit fast because you told me that you know, okay? So you told me that you know, and I'll be a bit fast. And I have a review, you know, I have a review, and so all details are there. Okay? So we are going to discover this anomaly in the Dirac theory. Okay? So I have a 1 + 1 dimensional Dirac. Okay? So okay, and what is it? Well, the action is dt dx psi bar okay. So it's massless. Gamma matrices are the Dirac gamma matrices. They obey okay with which is diagonal of plus minus okay. And so I have that what do I have? I have that what do I have? Yeah. I can write them in terms of Pauli matrices. So I have gamma 0 sigma 3, which makes gamma 0 square equal to 1, and gamma 1 is I sigma 1, which makes gamma 1 square minus 1. And also define gamma 3, which is gamma 0, gamma 1, which is sigma 3. Okay? Okay? So this theory has two conserved charges because there are two gauge symmetries. One is, so this is a two spinor, okay? It's a two spinor. So there are two symmetries, U1 normal symmetry, which is psi, which goes into e to the I lambda psi, and A mu goes into A mu plus D mu A mu. This is a gauge symmetry, so it depends on X, okay? And the current is J mu. You can read it. J mu is gamma mu psi bar psi, okay? But there is also another. So this is gauge symmetry. But there is also a global symmetry, a second symmetry, which we'll call U1 twiddle, okay? Which is psi, which transform e to the I gamma 3 lambda twiddle psi, and psi bar, which transform psi bar e to the I gamma 3 lambda twiddle. And this is the axial symmetry. Axial symmetry, and the corresponding Current is J mu is psi bar gamma 3 gamma mu psi. Okay? Yes?
Gamma 0 is same as gamma spring.
Sorry?
Gamma 0 is same as the gamma spring.
Oh, I made a mistake. No, sorry. Sorry. I made a mistake. Gamma 0 is sigma 2. Not sigma 3. Sorry, I made a mistake. Yeah. And okay, so why is that you have two symmetry? Well, because in fact you can split the fermion in two parts. Okay, you can write the fermion in two parts, which are plus minus, and which is 1/2. Okay, and if I use this basis, you see that if I use this basis, you see that this is psi plus is the upper part and psi minus is the lower part. Okay, and the Hamiltonian split the Lagrangian split in two parts. Psi plus D is what? Well, D is okay. Split in two parts. In fact, these two parts they are left moving and right moving because you see this is dt plus dx and this is dt minus dx. So they are in fact two components. They have in fact kinematically different. One is a wave going one direction, and one is a wave going in the other direction. So each of them has a U1 symmetry, independent, and so these two symmetries are linear combination of the positive and negative U1 symmetries. Okay. The component are called, this component is called chiral fermion for chiral fermion. I mean, more precisely, chiral fermion would be the one in 4 dimension, but we adopt the same name here, okay? Same name. Okay. And so also the Hamiltonian splits in two components. Pi plus. Okay? Split in two components. Yes? Okay, so what is canonical quantization? Canonical quantization is to expand the field into the eigenstates of the Dirac equation, which is the equation of motion from this is d slash or d mu gamma mu psi equal to 0. Okay, you can solve it. It can be solved in the following way by choosing the gauge A0 equal to 0. So this is very convenient. So this Hamiltonian is in the gauge A0 equal to 0. I mean, like a previous non-relativistic problem. Okay. So now you have eigenstate. You have eigenstates which are plane waves. Okay, and you don't have to bother about the spinor because I just decompose into scalar thing. So you see the gamma function have disappeared here. So these are just complex numbers. I decompose them, and so I have the wave functions. Okay, so from the wave function I can write a field, which is the field is expressed in terms of solution of the wave equation with coefficient which are become creation annihilation operators. Also, let me put the length is periodic boundary anti-periodic boundary condition. So I put the length 2 pi r, which could be will be convenient later, and so the gauge field is periodic. And the fermion is antiperiodic. Okay, as before. So then I have a quantization of a momentum, which is okay. You see, nice thing that in one dimension you can solve in this gauge. You can solve by just ax. Ax is a constant. Basically, is a constant or depend on t. Depend on t. Ax, as we said the other day, ax is function of t. So you can solve for any ax. Okay? If you plug this solution into the, I mean, you can do both ways. You can impose the commutation relation between fields, and then get the algebra obeyed by this creation annihilator operator, or vice versa. You assume creation annihilation operators, okay, and get the commutation relation, which is canonical quantization, psi plus or minus xt, psi plus or minus x prime t, anticommutator equal to delta of x minus t. Okay? This commutation relation is equivalent to and the other are zero, okay? So the two components are split and each one has a anti-commutation relation. Okay? Okay, now we come to the problem, okay? There is a problem because now we have an infinite Dirac sea. So we have a spectrum like this. So let's discuss first A equal to 0, okay? Then we will recover A later, okay? We have a spectrum like this. So the velocity Vf, which will be, in relativistic will be c, but in general, in condensed matter will be some constant, is put to 1, okay? The velocity. Okay, now you have a infinite direct c, okay? And to be precise, we have to say that because of this 1/2, due to antiperiodic boundary condition, there is no state here, but there is a state here, 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 here. Okay, they are filled, and then these one are empty. And the Fermi surface you put exactly to 0. It's in between, okay, because you see, okay? Okay, now we have the problem that this quantity which involve the Dirac C have to be redefined because it's infinite. Okay? Okay? So, first of all, we define what is this fielding. What is this fielding? The fielding of a Dirac C. Well, it is Ck ground state equal to 0 for... Okay, let me now discuss one chirality. So now I discuss because the two are similar, okay? So let me take the plus branch and discuss how to define the theory on this branch, and then we discuss the minus branch later, okay? Okay? So I suppress the plus and minus now because they will be the same, or almost the same. Okay? And so this is Ck equal to 0 for k bigger than 0, and C dagger k equal to 0 for k equal to 0. So 0 is field, okay? So this is 0. Is field, okay? Because you try to add an electron where it's already there. There is no spin here. So you can put 2 and you get 0. Instead, this is empty, okay? So this is a definition of the ground state. Okay? Okay. Now we are going to define the currents. Okay? So what is the current? Well, from the classical thing, you know that the currents, let me define the moments of the current, are bilinear, okay? Okay? If you insert a thing, you will get sum over k okay, plus or minus. Okay, I get this infinite sum, okay? In particular, rho naught is a density, okay? The charge is integral of rho naught, okay? Which is okay? Well, now we have a problem because this charge is infinite, because when you apply to the lower, okay, you get that this is the charge defined like this, applied to the vacuum. So is sum over 1 from k equal or equal to 0. Okay? Okay? So what is the idea now? The idea is that you do so-called normal ordering. That means you remove this value of the charge of the ground state, because in fact you are interested on excitation around the Fermi surface, the excitation about the ground state. So you don't care about the charge of these states. Okay? You only want to know the charge of fluctuations of the ground state. Okay? Okay, and so you redefine the ground state, you redefine the operator by like this, okay? Rho 0 goes into rho 0 minus okay? In such a way that you call this normal ordered rho 0, in such a way that rho 0 normal order on the ground state is 0. You remove this part, okay? Hmm? Yes, please. Yes? The same.
And what is K equivalent K of K, C of K and N? Because before C was the value just on one index.
Where?
Above in the platform, C depends just on one index. Okay. And this is a K minus N or K? This is K minus N.
Yes.
Yeah.
You know, you put A, so this is A plus A x equal to 0. So I put the gauge field data, okay? Okay? More questions?
We don't have an equivalence in the graph of the definition of rho plus minus.
What was the question?
So in rho plus minus n, we have the integral expression. In order n, shouldn't we have?
Sorry, there is an n here missing. Fourier modes, okay? Fourier modes of the density. Okay? In particular, the zero mode is a charge density, and it has this problem. So what is the meaning? What is the that's a good point. Good point. So what is the meaning of these rho n operators? Rho n operators, they create a particle all excitations above the ground state. You see? So, for example, let's take rho minus n. Rho minus n with n positive. Well, it takes any state at value k and brings it to k plus n. So it makes this kind of jump. Okay? And the jump is delta k. The jump of k is delta n. Okay? So this creates a rho minus n creates an excitation. Okay? If it is possible, because if you start from here, so that's a sum over all k, so all positions, okay? So if you're here, you cannot create because it's already filled, okay? So now you go. If you go above here, you cannot create anything because it's empty. So these operators rho n, they all act for finite n. They all act around the Fermi surface, okay? Because otherwise they are zero. Either they are trying to make transition below where everything is filled, or they try to make transition where above everything is full. Okay? So then if you take n fixed, they are transition, particle, all excitations, that are given by the value of n, okay? So rho n, for n different from 0, rho n needs no regularization. It's well defined object because it will be, anyhow, there will be a finite, for n, for given n, there will be at most n terms in which the operator is non-zero, okay? Instead, rho 0, it takes any particle and put it back to itself, and here there are infinite, okay? Yes?
We get the rho plus minus n by integrating something out of x. So there is no x dependence there. Therefore, for capital Q, we integrate it out with x again. So rho doesn't have any x dependence, but in the next line, we integrate it out with respect to x.
Oh, yes. Sorry. What was it? What did I wrong? No, sorry, there is no integration here. Yes, it's already integrated. Yes, yes. Yeah. Okay, so what is the meaning of this subtraction in terms of operators? You can say that normal ordered is normal order of these operators, and normal order operators is only affects when you have the same index, so that in this case they don't anti-commute, and the normal ordering. So this subtraction amounts to, you can check, amount to saying that C dagger K CK normal ordered is C dagger K CK for K bigger than 0, and C dagger K CK is equal to minus CK C dagger K for K less or equal to 0. You see? So if you do this, okay, you see that the first operator acting for K bigger than 0, where it is empty, it is C, so it gets 0. Instead, when K is less than 0, which is filled, the first operator acting is C dagger, which is 0 again because it's filled. Okay? So this prescription is normal ordering equivalent to this. Okay? So there is, so you see, there is nothing arbitrary here, because once I define the my feeling of the ground state, everything is fixed. And it's kind of natural to require that the charge of excitation is 0 on the ground state. Yes, please. No, sorry. What is it? No, it's yes. Yeah. You subtract expectation value, okay? Yes? Yes? Rho n? Nothing. Nothing. Okay, so let's put okay. So, okay. So we have to stop. Because, so, okay, that was the definition, okay? So now I have, an ambiguous way. I've shown you quantization. Quantization amounts to substitute solution of the equation of motion, okay? And then establish this anti-commutation relation, okay? Then we had the problem of the infinite Dirac sea. And we solve by subtracting this piece. Okay, subtracting, which is makes sense because I want to study properties of excitation around the ground state. I don't want to care about the fact that the ground state is filled with all these particles. Okay, so this is an ambiguous definition of the quantum theory. Now we are going next lecture to discuss where the anomaly is coming from and what are the consequences. You already know the result because I showed you before that I show you the I show you the I show you the non-relativistic theory. Okay, I show the non-relativistic theory in which you had a finite number of particles in the Fermi sea, and so this theory had already a natural cutoff, ultraviolet cutoff, because the number of electrons in the Fermi sea is finite. Then I send n to infinity in this system, I get the same problem, because anyhow, even in a non-relativistic system, I will have to define quantity for excitation around the Fermi surface. This in a non-relativistic system, the number of electrons will be some big number, 10 to the 10, 10 to the 20. So there is this problem also in the non-relativistic theory, okay? And it is solved the same way. The new thing is that the relativistic theory, the two branches are independent. Here instead they are connected, okay? Okay, stop. Maybe we don't do a very long interaction, okay? Interruption.